Cool. Hey everyone, welcome in. Race Summit this year is exciting and I'm glad to be here. So my name is Kourosh, I lead the LM team at Anyscale. Together with Seiji, we're going to be talking about serving large sparse MoE models, in particular with Ray and vLLM. Cool, so let me give you a little bit of story of like the rise of sparse mixture of experts. So pretty much like any other deep learning idea, the core theoretical foundation was laid out in like 90s, and it was just forgotten until very recently, maybe like a decade ago, people started revisiting the same ideas in the context of transformers. So the real rise of MoE models, essentially you can attribute it to when like Mistral AI open sourced their mixture of expert models. That really culminated a lot of engineering innovation, resulting eventually in DeepSeek v3 moment, where it was a big milestone in open source, and it kind of like break out all the previous assumptions about how costly developing and serving these large models were. So two key insights came out of that moment. One was on the training efficiency, which was assumed previously largely believed to be very expensive. It turned out that you can actually do it very efficiently. And also on the serving side, DeepSeek team has started open sourcing their deployment model, and it was really great to see like how much of margin exists there to make a profitable like inference business out of inference. So today we're going to be focused on serving efficiency for this talk. And in particular, there are like three main enablers that we're going to talk about and how we're going to do them in RayServe. So there's one YDP, wide expert parallelism. That means distributing experts across many nodes, pre-fill decode disaggregation, and LLM-aware request routing or load balancing. All of these key ingredients are supported in RayServe LLM today, and are modular in a way that you can compose them with each other to kind of make this serving pattern happen. Cool. So what really makes MoE models cost efficient? To answer that question, we have to contrast it against dense models. In traditional dense LLMs, for every token, when you do a forward pass, all of the parameters in the model are getting activated, which means as I increase my batch size, my compute that I'm spending for forward pass is going to increase proportional to my batch size. However, in mixture of experts, there is this mechanism routing, and basically what it does is that during forward pass, you only activate a subset of experts. And this way, as you increase your batch size, your increase in compute is going to be sublinear to your batch size. But to really capitalize on this sparsity, you need to increase batch size as much as possible. So the gains of this mixture of experts show at high throughput regimes. Before I go any further, I just want to align ourselves on how do we measure a serving system efficiency. So in serving systems, we are oftentimes like looking at two things. One of the most important things is interactivity. That would be like how fast your response is coming back, often measured in time per output token, time to first token, and such. Different applications have different requirements on this SLA. But then subject to this SLA, what we want to do is maximize some sort of efficiency metric. That would be like something like dollar per token spent, or like some sort of throughput measure per GPU, something like that. Usually to see this concretely and compare different serving systems to each other, we plot this graph, where on the x-axis you've got some sort of interactivity SLA measure. That would be like tokens per second per request. And on the y-axis, you measure efficiency, token per dollar or like token throughput per GPU. A typical system will look something like this. As you increase batch size, you're sacrificing a little bit of SLA, and in return, you gain throughput. But after some point, increasing batch size doesn't necessarily mean like getting more throughput. So it saturates. What we want is a serving system that pushes this curve up to the right, and we want to see how we can achieve that. So one of the bottleneck, like one of the key things we want to do in an inference system is maximize batch size as much as possible so that we can push this like saturation regime up. Now let's see what blocks us from making batch size indefinitely large. The biggest factor is KV cache size. So this figure illustrates where a GPU memory would go when you serve a model. So you've got like model weights, CUDA graph, activations, and they consume some memory. Whatever is left is going to be left for KV cache, and that determines your batch size. It's effectively how many requests can I concurrently serve and store in a KV cache. Now, the question is, how can I increase the KV cache of my when serving a model? So one of the ways to do this is incorporating model parallelism, like tensor parallelism. By doing tensor parallelism, you're reducing the amount of memory you need for model shards on that GPU, and effectively CUDA graph and also activation, and whatever is left is going to be attributed to KV cache. So now, by spending more resources, I can increase my batch size, but the question is it going to be worth it, right? Meaning that I'm spending more resources, I'm gaining batch size maybe 2x. Does that like actually result in more efficiency when you normalize it? Maybe it's 2.5x. That would be better, right? So basically the key question is, by doing more parallelization and like different parallelization strategies, I unlock KV cache, but does that ultimately result in the better throughput overall? Cool. So one of the key ideas behind DeepSeek was using multi-latent attention, which directly correlates to using KV cache more efficiently. So we want to kind of like get a 101 on what MLA does and connect that to what we're going to talk next, right? So to understand what MLA is, you have to contrast it to multi-head attention. So in classical, like in transformers, you've got essentially QKV matrices. I assume the audience know how attention operates. You've got these matrices, and they're organized in different heads with independent values from each other. And what you want to do is during inference and during decoding, you want to store these KV units so that you don't have to recompute them. So this, like this surrounded, like this dashed line essentially shows the amount of bits you have to store in KV cache. In MLA, however, what you have is essentially the same QKV, but during training, you learn a compressed representation across all the heads. And what this unlocks is that during inference, you don't have to store all those bulky KVs. You can only store the latent across all the head. So to put concrete numbers on it, DeepSeek v3, the latent essentially is 70 KB per token, whereas for some models like Llama 405B, this amounts to almost 7x more per token, which means I have to spend more KV cache size to store any token. Now, let's see what happens if you want to do tensor parallelism on an MLA architecture. So in tensor parallelism, I shard part of my models, part of these operations across 2 GPUs. So I can do that for QKV. It's fine. But when I get to MLA, because it's only like a latent, not shared across heads, I cannot really split it. There's not much benefit. So what I do instead is I replicate it. But this directly defeats the original purpose of increasing batch size and using the aggregate GPU memory that I want to get out of like using multiple GPUs. So what you need to do instead, so yeah, this one is also important, which is like you're sharding part of the model that is only a fraction of the total number of parameters in an MoE model. So the attention counts around like 2-3% of the entire parameter count of an mixture of experts. So you're effectively just sharding this part, right? So one idea is to incorporate data parallel attention instead, which means like any other data parallelism strategies, you replicate the attention parts, but instead of sharding your request, you shard your request across batch sizes, which means for each DP rank, I'm going to get a different set of KVs for different requests. Now, to see how this plays out, we ran some experiments to profile the GPUs. So here, you're seeing like a DeepSeek V3 model getting served on TP8, DP8, and DP16 for demonstration. And what you're seeing on the y-axis is, for each case, how is the allocation of memory per GPU. The important part is the KV cache size that I'm spending. So TP8 requires 35 gigabytes per rank. DP8 is 10 gig, and DP16 is 44. That is the amount of KV cache that you can get by doing this type of parallelizations, right? Now, the key idea is that TP8, when you add more GPUs across the group, like 8 of them, you have an aggregate GPU memory of 35 for the entire 8. But for DP8, this can get aggregated. So you get 10 times 8. And then for DP16, you get 16 times 44, right? So if you map this back to how many concurrent requests can I serve on a given, let's say, input token length, so that would be the last column. You can see that for TP8, I can only serve 92 requests concurrently, where each request has a size of like 5,000 tokens. But when you do DP8, you can get almost 2.5x more capacity. And then for DP16, this is going to be 10x more. This is the true magic of doing DP with MLA, which allows you to increase your batch size to 10x, to 5x, or however you're like, and that increases proportionally with like your DP degree. Cool. So how do I do that in RayServe? So wide expert parallelism is essentially another word for doing like this deep DP with expert parallelism. So on the right-hand side of this slide, you can see a snippet of code that shows a compact representation of how it would feel to deploy something in vLLM that does DP. So we have an LM config. I'm describing, I have DeepSeek model. I say, OK, there's engine configs, there's data parallelism there. And I describe some like environment variables. Then I have essentially build a DP deployment, and then I connect ingress on it. The benefits of this stack over Kubernetes native solutions is that it really separates infrastructure from application. So if you're deploying a model and everything around the application stays in Python in your hand during modification, and you don't have to deal with like YAMLs and CRDs and et cetera, where your serving pattern gets complex. It has built-in observability, and iteration speed when you're doing benchmarking is going to be way faster than changing YAMLs and like restarting pods. Cool. So let's see what happens in RayServe when we use YDP. So this is an example of DP2, TP2, EP4. So at the foundation of this, we have a Ray cluster running anywhere. It can be on Anyscale. It can be on Kubernetes. And when we instantiate DP2, each vLLM instance is going to be deployed as a serve replica. Serve handles request routing, which means whether it's like KV cache affinity routing or like power of 2 or round robin, it does that for you. Within each engine, we have essentially TP2, which means I have to essentially coordinate 2 GPU workers and we orchestrate them through Ray. Within each executor, you have KV cache units, which are TP sharded across DP groups. Then you've got attention, like QKV matrices that are TP sharded in each DP group and replicated across DP groups. Experts are going to be sharded across both TP and DP groups. And then between attention and experts, you've got these all-to-all communications, which dispatch and combine tokens after each stage of experts. So what these units do, essentially, they're routing tokens between attention units to the corresponding experts that they should get routed to. This architecture is very cool. It scales to a large number of GPUs. And the more you scale it, you reduce the number of experts per GPU, which makes your gem operations much more efficient and like your GPU utilization higher. Cool. So now I hand it over to Seiji to talk about some of the problems we encounter when doing this.
Yeah, cool. So Yeah, as we know in systems, there's no free lunch. So while EP can give us a lot of throughput benefit, we need to balance out these additional collectives that are necessary to coordinate the ranks. And so one issue that you hit right away is trying to unify prefill in decode. So as these ranks are executing, they can no longer execute independently like you would in a normal data parallel deployment. You have these shared experts, and a request's tokens might be routed to any other rank in the deployment. So they need to be executing kind of in lockstep or having collectives after each layer. And what that means is that you could have ranks, if the naive or mixed deployment, you could have ranks doing prefill, long prefill, continued bound prefill, decode, or with no content at all. And the effect is an exaggerated synchronization overhead in expert parallelism. So that motivates, for one, the initial hypothesis or thesis behind prefill disaggregated serving. And then after that, you also want to do load balancing among the ranks and make use of your hot prefix caches if you are in your prefill deployment. So that's one solution to this issue of unified prefill and decode. And the other is that unifying prefill and decode, you miss out on the optimizations at the kernel level. So you can optimize the DPP kernels are optimized separately for prefill and decode stages. The low latency kernel is optimized for decode and high throughput for prefill. And so you're basically leaving performance on the table without using the specialized kernel. And then another reason that didn't make it onto this slide is also usage of CUDA graphs. So the vLLM attention backend doesn't support the piecewise CUDA graphs for Flash MLA, for example. And it also causes a big performance hit. Recent testing went from, so with like pure torch compile graphs, my teapot was like 800 milliseconds. And then when I switched to a disaggregated setup, started hitting the CUDA graph, it went down to 200 milliseconds. So really huge benefits to be had from CUDA graphs for one, and then general disaggregated serving after that. And so what would that look like with Ray-serve LLM? Or illustrating what disaggregated serving looks like for anyone who's not familiar. Basically, you separate your prefill and decode engines. So when we're serving a request, we'll route it initially to a prefill engine, which will compute the KV cache, and then use some connector, in this case, it's Nixel, to send the KV cache to a decode engine that will be optimized to handle the rest of the output sequence. And in Ray-serve LLM, we have a builder pattern for this. On the top right, you have the prefill config. This can specify your number of replica ratio, any particular engine keyword arguments you might want for prefill, independent from decode in the bottom. And then we have a builder that you can use out of the box to put them together and serve the application. And our goal is to just really commoditize this and make this pattern available to anybody that wants to use it. So what does the performance look like when we actually try this? This is kind of a case study that shows the borderline or overlap where disaggregated serving could be useful compared to like the naive baseline of just tensor parallel replicas on the same hardware. So in blue, we have the Pareto frontier for disaggregated serving. And then in red is the 2x TP4 baseline. And then it's the same y and x axis as before, throughput versus interactivity. The labels are kind of small, but in the bottom right, you have the lower concurrency regime. So it goes down to concurrency 4. And then as you go up to the left, it's higher concurrency. And so basically what the graph shows is that the Pareto frontier for disaggregated serving can offer higher throughput at higher batch sizes, with better interactivity at higher batch sizes. But for this particular workload, you might be taking a hit at lower concurrencies compared to a 2x TP4 replica. So the takeaway from this should just be to really profile your workload, think about what you're serving, basically what your concurrency is, to make the call if disaggregated serving is actually worth it. And then, of course, so this is, I didn't mention, but this is a 5,000 input token length, 250 output sequence length, output token length workload. And if you started to boost that input token length up, you'd see more benefit. And then also want to just make super concrete the impact of the transport backend. So these KV cache transfers have to be fast for this to really work. In blue is an intranode disaggregated serving deployment. This is over NVLink. In green is internode over EFA, and then red is Ethernet, so just over TCP. And you can see that your throughput totally gets killed if you try and do this over a transport backend that's not fast enough. So you really need to think about, or just be mindful if you're trying to deploy something like this, the hardware needs to be able to keep up. Cool. And then I touched on request routing as well. This is something that we have in Race or vLLM, but not only do you want to you want to maintain the load balance among these EP ranks, and also do that in an LLM-aware way to make use of that KV cache, whether you have long system prompts or your some ongoing chat, multi-turn chat that you want to reuse the KV cache for. We make it pretty easy, I hope, or we try to make it pretty easy to deploy this. You can do this with we have a prefix tree actor that basically records the content of requests that come in and are serviced by the deployment, and then subsequent requests are compared and matched against the prefix tree to serve to basically an approximation of the KV cache content for a particular replica, and make use of that prefix cache that's available in vLLM. And you can do this with just adding to your LLM config with a request router that's built in. This is a collaboration with RayServe, actually, and so while we do have this built-in prefix cache affinity router, you can make your own and plug it in without making a PR if you want as well. And so what is the impact? On the right here, have two plots of, on the top right, prefix cache hit rate, and then on the bottom is total throughput for comparing the prefix cache-aware router and random power of two choices router. And the x-axis is scaling replicas. So you can see that maintaining the prefix cache-aware router maintains prefix cache hit rate pretty high compared to random routing as you increase the number of replicas. You get a lot of benefit for a lot of benefit compared to this additional overhead of a prefix tree. Cool. So adding it all together, what does it look like? You'd have something like prefill configuration. It's easy to do in Race or vLLM. You have a prefill configuration, specify Nixel, and environment variables that you want, specify the high throughput EP kernels, add prefix cache-aware routing, and then similar for decode. Super modular. I think that, yeah, as Kourosh mentioned earlier, you can do this without having to think hard about your infrastructure, or rather, if there are special labels that you want to add, that's possible. If you want to reuse your code or deploy multiple applications with the same builder pattern, you can do that really easily, all in the same file, which I think is a big benefit. And then I also want to give a brief shout out to the Ray dashboard. When I was new to Ray, I was pretty surprised that we had such a nice thing. But it makes it easy to deploy these things when you're first bringing it up, know what's going on. Definitely check it out. We have LLM-specific metrics available via dashboard as well. Cool. And so you might be wondering, OK, going through Ray, is there a big overhead, or am I going to pay a performance penalty if I try and put this in production? And so that's something that we're always working on in benchmarking and wanting to make sure that Ray stays performant compared to standalone vLLM deployment. And this is our latest test, EP16. You can see that we have very comparable performance to vLLM. On the right-hand side is tokens per second per GPU, vLLM in green hitting around 2,100 tokens per second per GPU, and we get very similar performance from Ray. In the work in progress, again, we're working on making sure this can keep up at DPP 32 and beyond. Wanted to make sure that we can hit those same numbers. And yeah, this was taken on Anyscale, by the way. Cool. All right, so in summary, what our big takeaways that we want you all to have today, that DP, EP deployments can really improve your throughput at higher batch sizes, but they can be complex to put together and deploy. You need request routing to make the most out of that KV cache storage or KV cache savings. And that's all available today in Ray Serve LLM. And also that Ray Serve LLM in general can be used to glue together these primitives and build up whatever complex performant patterns you want to do, while still having nice paved paths for the more simple stuff. Looking forward, there was an awesome talk by Ray yesterday about adding elastic and fault-tolerant YDP. Looking at LLM-aware auto-scaling, thinking about, we know folks want to do auto-scaling based on things like tail latency or TPOT or TTFT, and that's definitely on our radar. And then just generally improving user experience for stability, reliability, whatever your workload is. So whatever that is, yeah, we'd be really interested to hear from you, think about what you are using Ray Serve LLM for, what you'd want to use it for, and to that we invite you to do that via Slack. Thanks. Cool. Any questions? Yes.
There's one.
Oh, sure.
I'm curious about any experiments you guys have done with parallelism in multi-head
Pipeline.
Pipeline
the question
parallelism?
was any experiments we've done with pipeline parallelism.
Great. Should I answer?
Yeah, go for it.
So yeah, the question just, I'm going to repeat, have we done any experience with pipeline parallelism? Yes. Pipeline parallelism essentially can gain you certain throughputs, but it's not as good as DPP. Because mostly you have bubbles and because you still have mixture of prefill and decode, where prefill can essentially still create bubbles for decode, and then you have this activations moving from one node to another. DPP usually dominates the throughput of that pattern, and I think it's the way to go for these larger scale MoE models. All 12.
If that's not available for whatever we're working on with the hardware, for example, we have some pipeline parallelism.
Yeah.
Any sort of, because in my experiments with pipeline parallelism in my hardware, we can get issues with, Ray channel errors, communication issues. So I think I'm at least my prototyping having trouble figuring out where that's going to go.
Got it.
Well, even with, so the question was, okay, if DPP kernels aren't available, you don't have, you can't use NVSHMEM or something like that, what could you do instead? I think you can still try the all gather, reduce scatter backend, all to all. So that's built into vLLM and just uses nickel, which I think should, yeah. So you could try that. It's less effective, so it doesn't, you don't get the per expert routing of DPP kernels or the other coup de grace optimizations, but it could be worth a try. In general, though, without InfiniBand, it's our experiments. Yeah.
InfiniBand
Okay.
is there, just you can't get too much of the hardware itself. But
Sure.
It's I guess what I'm trying to narrow it down to is a P2P communication with pipeline parallelism. With your talk on disaggregated PD, there might be something going on with the scheduling. Just looking for any insights to help me, but
Okay.
I guess
Yeah, maybe we can talk in the hallway.
Yeah.
Anything else?
Just a simple question. Have you tried running MoE-based quantized model, and is it worth doing DPEP on those quantized models based on the MoE, or is that a big loss? Or?
Yeah, so quantization just is orthogonal to this approach, right? So If the question is it still worth it, like this essentially makes your GPU utilization better because you reduce the number of experts per GPU, and then like all the SMs can just load the experts that they are supposed to work on. And since there's not that many of them, they just like you avoid moving, data from memory to the SMs of the GPU. So like data stays there, throughput goes higher, so your utilization becomes more like compute bound pattern. That same story holds when you do, FP4 on B200s or whatever. Even though your model is quantized, you may want to use these to really like capitalize on the compute efficiency of your GPUs.
So it's not exclusive.
It's not an exclusive pattern.
Okay, cool. Let's talk in the hallway if you have any questions.